So today our topic of discussion is energy dissipated by viscous damping. So WD is the energy dissipated by damping in a cycle. So suppose there is a spring mass system with a viscous damper and which is subjected to a harmonic force this, and the displacement is this, the velocity is this, and Fd is the viscous damping force. So Fd is Cx dot. So Cx dot means C into omega x cos omega t minus phi. So what is the energy dissipated in a cycle? That means in a period actually. So WD is, so this integration sign is actually integration over a cycle, Fd dx. Or if you now take dx as dx dt dt, so this is Fd dx dt dt, and it is from 0 to capital T, where capital T is the period. So Fd is from here, Fd is C omega x cos omega t minus phi, and dx dt is x dot, which is omega x cos omega t minus phi. So C omega square x square can be taken out of the integral, and what remains inside is cos square omega t minus phi dt. So this is C omega square x square. Now just we are changing this variable to dt to d omega t, but here just though we have made this change, so it should not be like this. It should be when t equal to 0, omega t is 0, and when t equal to t, omega t is equal to twice pi. So this is actually from 0 to twice pi. So now if you integrate this, you get pi c omega x square. So I will make a little change in this. So this is, since we have made a change in variable, we have in place of t we are using d omega t, in place of t we are using omega t. So the limits of integration would be 0 to twice pi. Okay. So omega WD is pi c omega x square. Now see, for viscous damping, Fd is c omega x cos omega t minus phi, or c omega x cos omega t minus phi under root is sine square is cos square omega t minus phi, which is 1 minus sine square omega t minus phi. So c omega x square minus this, and this is small x. This is small x because small x is this. So x square minus x square, or c omega. Now again we take back capital X, so it is 1 and it is x by x square. So now if you divide Fd by this and take square, so you get this relation. That means this is the equation of an ellipse if you plot Fd along this axis and x along this axis. So f goes up to c omega x. So this point is obviously c omega x, and this is, and x goes up to x. So another way of expressing this graph is, in place of fd you just plot fd plus k into x. So kx is actually a straight line like this, where the slope of this line is k. Now suppose you take this x, suppose this x, so this is fd. So at this x you just with kx you add this value, so this value is same as this value. So this is kx, and with this you add what you are getting here. So in this way for all points you can do it. In this way for all points you can do it. So here you add this much. So in this way you get this plot, and the area inside this graph is, as you know, the area under an ellipse you can find out, and that is same as, and that has to be pi c omega x square. And if you think of a spring mass damper like this, then actually kx plus cx dot, so for viscous damping this is cx dot plus kx is actually the transmitted force. So it is easier to measure the transmitted force, so it is easier to construct this graph. And since this the area enclosed by this graph, which is the hysteresis loop actually, and area enclosed by this hysteresis loop is same, it is easier to draw this. So this graph is preferred. So here you can just think of an experiment like this, where this is a simply supported beam. So here of negligible mass, a simply supported beam of negligible mass, simply supported, and at the center you put a mass m, and here the stiffness, so this and this support you put on a bar with a force sensor inside, so that you can measure the support force when you excite this mass by an exciter. So this is an exciter, and this applies a force on the midspan of the beam, where the mass is placed at the midspan of the beam, and a force is applied at the midspan of a beam, which is a harmonic force of the form F naught sin omega t. And due to the deformation of the spring, due to the dynamic displacement of the spring, there is some support force coming, and the support force is being measured by these force sensors. So now the beam can be modeled by a spring and a damper in parallel, where this k is 48 I by L cube. This is the mass, this mass is this mass, and this is the excitation force, and the force transmitted to the ground is kx plus cx dot, and that means this force sensor measures half of kx plus cx dot, and this force sensor measures another half of kx plus cx dot. So it is easier to measure kx plus cx dot together, and it is difficult to measure it separately. That is why I told that the second graph is preferred, and it is easier to draw the second graph from experiment. So here you remember that hysteresis loop is elliptic in shape when energy dissipated per cycle is proportional to the square of amplitude, which is true for viscous damping. The energy dissipated per cycle is proportional to the square of the amplitude. Now for viscous damping, the energy dissipated per cycle is this. For other type of dampings, the energy loss per cycle can be equated. There the hysteresis loop may not be for other types of damping, and in general will not be elliptic, but whatever area we are getting under the hysteresis loop can be equated to pi c omega square. Suppose the energy loss per cycle in other type of damping is WD, and WD is the area enclosed by the hysteresis loop. The hysteresis loop is in general not elliptical, and that can be equated to the energy loss per cycle in viscous damping, and from here we can find out the equivalent viscous damping coefficient. And this equivalent viscous damping coefficient can be used to find out the amplitude at resonance for cases where the damping is not viscous in nature. So this is a way to approximate other type of damping by viscous damping. So, and here you see in the graph, this is the graph taken from the lecture on forced vibration, where a spring mass system with a viscous damper is subjected to a harmonic force. Here you see when the damping is actually 15%, 10%, 5%, there the actually the damping matters near the resonance. Away from resonance, the effect of damping is not much. So if we can calculate the amplitude at resonance by this approximate method, then at least with a reasonable accuracy, then it will be of much use, because actually this damping is more pronounced near the resonance. So if you can find out the resonant amplitude correctly by this approximate damping, or reasonably correctly by this approximate damping coefficient, then this model is of use. This approximation is of use. So now here we we will work out one example. So bodies moving with moderate speed in fluid such as water or air are resisted by a damping force that is proportional to square of the speed. This is the body drag, and determine the equivalent damping for such equivalent viscous damping actually for such forces acting on an oscillatory system, and find the resonant amplitude. So here suppose this is the, we assume that again the body is moving in a harmonic way, that is x equal to x cos omega t. It is same as x equal to whatever you select, you can select x cos omega t or sin omega t, whatever. The next dot is like this, okay, and the damping is here actually, damping is actually, see this is the mass, and here in this direction x dot and x double dot. So the damping force is in this direction, and the damping force is alpha x dot square sin x dot. This is sin x dot. Sin x dot means sin x dot is equal to 1 for x greater than equal to 0, and sin x dot equal to minus 1 for x dot less than 0. So this is the sin x dot, or you can just remove this. So that means if this is x dot, this is x dot, this is x dot, FD is like this. This is actually alpha x dot square, because the negative part of x dot, when you square it, it becomes positive. So this is alpha x dot square, but the damping force need to be negative in this half, where the velocity is negative. The damping force should also be negative. So you just add a sine of x dot. Since the sine of x dot is negative here, this becomes negative, and the sine of x dot is positive here, so this becomes positive. So this becomes the damping force. This becomes the damping force. Now so this is the damping force. It's gone. Yeah, so this is the damping force. Now Fd dx is the energy lost per cycle, but instead of doing on a full cycle, so because the sin x dot is there, so we do it only for the half cycle and we multiply it by 2, assuming that, not assuming, because it will be twice, the loss will be twice in a complete cycle than what is lost in half cycle, what is dissipated in half cycle. So here, so in this, suppose from here to here we are integrating 0 to t by 2, so it is minus alpha x dot square dx dt. This is minus alpha x dot square x dot dt, x equal to x cos omega y2 we have assumed. So x dot is this minus omega x sin omega t. Now you integrate. So here this is the integration. Now here again it has to be 0 to pi, not t by 2, it has to be 0 to pi. So this is 0 to pi because half cycle, and this is the energy dissipated. Where is the mouse? Yeah. So this is the energy dissipated. So now this has to be equated with this. So your C equivalent comes this, and the resonant amplitude is F naught by C equivalent omega n. So in C equivalent we put 8 by 3 pi alpha, since this is resonance, omega equal to omega n, and here another omega n is there, so omega n square, 1 due to this and 1 due to this, and this is x is the resonant amplitude. So this x rays and this x rays becomes x square. So this is the resonant amplitude. So this is an example. So in case of viscous damping, Fd is Cx dot, which is a sine curve, but this is not sine, this is actually, though it looks like sine, it is actually alpha x dot square into sine x dot. So this is, so I have shown it, or the student who has taken these notes, this figure has been taken from one previous year student, so he has shown it in dotted line. Now the next example is of Coulomb damping. So in Coulomb damping you see, so suppose this is x sin omega t. Here one thing, that though this is a nonlinear type of damping, this is the nonlinear type of damping, as you can understand. So this is a nonlinear damping. So but we still assume that the vibration is harmonic, because the displacement we are taking as harmonic. So this is one assumption we are making. Here also we are taking the displacement as harmonic, though x dot is this and this is Coulomb damping, because Coulomb damping is like this, it's constant. So and as the velocity changes, again it is constant, and as the velocity changes, again it is constant. So we have already studied Coulomb damping in while we are studying free damped vibration, and here the total energy lost is, here see x is from 0 to maximum value it's going, so x is going from 0 to its maximum value downwards, and the damping force is upwards. So the force is against damping force is upwards, because Fd is positive upwards and x is positive downwards. So x is going from 0 to maximum value. So suppose this is the static equilibrium and x is going from here to here, and the damping force is acting like this. So as long as x is increasing from 0 to maximum, that is from here to here, the damping is like this. Then the damping then what happens, x goes from here to here. Then what happens, the damping changes sign and it becomes like this. So for this it is this one. So always that from here to here the damping is negative, where x is actually from its maximum, it is going to maximum on the other side. So maximum on the positive side to maximum on the negative side, and FD becomes negative and remains negative up to this. So the total energy lost is, and again for here, so because this is one period, it is going from here to here, and now FD becomes change like this, positive again, and where it is coming from negative maximum to 0, and this is this. So actually it is in a cycle, the total energy loss is this one. So this has to be equated with pi c equivalent omega x square, and this is the equivalent damping coefficient. So but here what we do, in place of just finding out the resonant amplitude, we just put it here in the expression for x. In the c we put the c equivalent value, which is 4ft by pi omega x. This omega and this omega gets cancelled out. So this, now we take it, multiply it with x and square it. So this is the right hand side square. So here this has got x square in the denominator, x square. So this gets cancelled out, and this we take in the right hand side, and now we write x as this. So now we non-dimensionalize this, or we divide the numerator by k and the denominator by k. So this becomes something like this. So x by f0 by k, or x by x static, is this. So one very interesting observation, or two very interesting observation, is that, see, the value within the root cannot be negative, because then it will become imaginary. So that means this 4fd by pi f0 has to be less than 1, or 4fd has to be less than pi f0. So 4fd has always to be less than pi f0, or fd has to be less than pi f0 by 4, otherwise motion is not possible. This is one interesting factor, at 4fd has to be less than pi f0. And another thing is that in case of Coulomb damping, at omega by omega n, the amplitude will be really infinite, because damping will not help you in any way. But in viscous damping we have seen that with this some plus thing is there, which actually limits the amplitude even at resonance. So these are two interesting observations. So let me stop here today, and in the next class we'll discuss structural damping. So thank you.